Now, I don't know how else to start off this video since I don't own a domino set to help you viewers visualize the topic that I'll be discussing. So I think I'm just gonna roll with it. I'll probably just put like a domino set like on my thumbnail, or just put it right here where my hands where my hands at. But maybe a ladder, I don't know. But don't worry, I'll explain why the domino set is a quintessential example to this topic. Anyways, mathematical induction. You've probably heard about this in a class. Maybe not, I don't know. But let me explain the history and the meaning behind this proof technique. First, the history. Early implicit traces can go back all the way back to Euclid's proof of the existence of infinitely many primes and Bhaskara's cyclic method, which was the method used to solve for indeterminate quadratic equations. So the earliest proof of the induction of arithmetic sequences was coined from al-Fakri, who was written by al-Karaji in 1000 AD, who used this to prove the binomial theorem and Pascal's triangle. So I only just gave you just a tiny portion of the origin. If you're interested in getting to know a little bit more about the history of this technique, then feel free to look it up yourself. I don't know too much information about this history as I'm not that knowledgeable in the subject of history in general. Secondly, the technique. Yes, it is a mathematical proof technique, but what does it really mean? To put it simply, it is used to prove that for some property, we'll call it P if n, holds for all natural numbers, i.e. n equals 1, 2, 3, 4, and so on. The proof consists of two cases to analyze in order for this induction to work successfully of a certain property. First, the base case. You must show that the property holds for the first natural number n equals 1. Second is the inductive case. You must show that the property holds for n equals k, which is known as the induction hypothesis. So once you've shown that, then you must show that the property holds for n equals k plus 1, which is the inductive step. Once you prove these two cases, then the induction works for specific properties and formulas. We say specific because not all proofs perform successfully just by simply relying on induction itself. So now here's the explanation of the analogy of dominoes. So imagine having a set of dominoes with you, and you're placing these dominoes so that the first domino falls into the next domino, and then falls into the next domino, and so on, creating this, quote, domino effect. This metaphor is exactly similar to the mathematical induction. From the base case, it is equivalent to assuming that the first domino will fall, just as n equals 1 holds for that property. For the inductive hypothesis, we are to assume that the next domino will fall after the first one, which is similar to assuming that n equals k holds for the property. And for the case of n equals k plus 1, we have assumed earlier that the previous domino will fall, in this case n equals k. But the bigger question that we have to ask ourselves is that, will the next domino fall if we assume that one of the dominoes will fall? That is the goal that we have to show for this case of n equals k plus 1. So once you prove all these cases, then it will be proven valid that the property holds for all natural numbers. So to put it in terms for the domino analogy, all dominoes will fall because you have showed that the first domino falls, and the next, and the next, and so on will also fall as well. Another analogy that is identical to the induction technique is climbing a ladder. You can definitely climb the first step of the ladder if by showing it, but afterwards now you must show that you can climb on to the next steps of the ladder and so on. So now let's take a look at a couple examples. Time to switch camera perspectives. Just a side note, before I continue on with the examples, my camera lens tend to frequently go out of focus, so I apologize for that in advance. All I can really say is just bear with it. There isn't really much I can do with it by the time I edit this video, so hopefully I can actually get this resolved next time. Anyway, continue on. Alright, so welcome to the new camera perspective, and now we're going to start off with the first example. So here's a popular induction example. So let's prove that the sum of the first n natural numbers is given by this formula. 1 plus 2 plus 3 plus dot 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 plus n equals to n times n plus 1 divided by 2. So first let's prove the base case, n equals 1. So we just plug into the formula, so in this case we have just substitute n for 1 is equal to 1 times 1 plus 1 divided by 2, and we would get that 1 is equal to 1 times 2 divided by 2, and we get that 1 is equal to 1. So the n equals 1 case is true. So now we have to show the second case, n equals k. So do the same thing as before. We have that for k, 1 plus 2 plus 3 plus dot 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 so on plus k is equal to k times k plus 1 divided by 2. So with that, let's actually make an assumption and assume that this is true for n equals k. So assume true. So with that, so now let's prove the following case for n is equal to k plus 1. So now with the following, we'll have 1 plus 2 plus 3 plus dot 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 6, ignore that part, plus k plus 1 is equal to k plus 1 and k plus 1 plus 1 divided by 2. So this is what we have to show for the n is equal k plus 1 case. So let's use the assumption that we have from earlier, n equals k, and let's substitute the formula. So we'll use the assumption case. So now we would have 1 plus 2 plus 3 plus dot 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 plus k, and now let's add the term for k plus 1 to both sides, such that, so we add the k times k plus 1 divided by 2, then we add the term plus k plus 1. So this involves some algebra that we have to do in order to solve to show that the case is true for k plus 1. So let's do that right now. So we want to have a common denominator for both so that they can be added equally without any trouble. So let's say this, so we can actually cross multiply by from your loss of fractions, we can actually cross multiply. So this is the same thing as saying k plus 1 divided by 1, so we can cross multiply from there. So we have 1 times k plus 1, and then over 2, then cross multiply from here to there, so we have plus 2 times k plus 1 divided by 2, because we have that both denominators 2 and then denominator here times 1, so they share common factors or common denominator. So k times k plus 1 plus 2 times k plus 1. So let's simplify that out. So now we would have k squared plus k plus 2k plus 2 divided by 2. So now let's simplify this out a bit. So now we have let's combine the like terms. That's what I meant to say. Plus 3k plus 2, then divided by 2. So what can we do from here? So exactly from algebra, if you remember, we would have to factor out, or in this case use the unfoil method, such that we have the terms x plus, or in this, my bad, k plus 2, and then k plus 1. See, if you remember from FOIL, you have to do case, you have to do the first, then your outer, then your inner, and then the last. K squared, right here, k times 1, it's k, then 2 times k is 2k, add those terms together, you get 3k, and then 2 times 1, 2. So this is exactly what it is. Now, if we can go back from earlier, we have this, so we can actually rewrite this. We can actually rewrite this a little bit differently. So now we actually have k plus 1, then times. You can actually group these in a different way. So now we have k plus 1, then plus 1 equals 2. So what do you have? So look at that. This is the same thing as this, and this is exactly the same formula that matches with this when we plug n is equal to k plus 1. So this means that n equals k plus 1 is true, meaning also n equals k is also true in this well. So by induction, the formula is true for all natural numbers. By induction. So there we have it. That's the first example. So now let's take a look at the second example. So here is our second example. Is 3 to the n minus 1 a multiple of 2? Or if you want to rewrite this a little bit differently, you can also say that is 3 to the n minus 1 equal to 2m, for m can be some arbitrary integer. So this is what we need to show. So now prove the base case. N is equal to 1. So let's plug n is equal to 1 to the equation. So now we have 3 raised to the 1 minus 1. Is it equal to 2m for 2 is some sort of multiple. So we have that 3 to the 1 is 3 minus 1, which is equal to 2, which is also equal to 2m. So meaning 2 is a multiple of 2. So the n equals 1 case works. So that's a check. So now let's show for n equals k. Simply just plug into the equation 3k minus 1 equals 2m. Now let us assume true. Let us assume true for k, n equals k, in order for us to prove for n is equal to k plus 1. So now let's plug in. And so now n equals k plus 1. So 3, then k plus 1 minus 1 equals 2m. Is it a multiple of 2? So by using by laws of exponents, you can actually split 3k to the plus 1 as 3 to the 1 times 3 to the k, because they share the same base, 3, which is the same thing as k plus 1 for the exponents. So equals 2m. So observe that we can manipulate 3 so that we have 2 plus 1, which is the same thing as 3, then all that being multiplied by 3k to show that, or I forgot to put a minus 1 here, put a minus 1, then a minus 1 equals 2m. So using the distributive property, now we have that is 2 times 3k, then plus 1 times 3k, which is just 3k, then minus 1 equals 2m. Observe over here 3k minus 1. This is from n equals k, so we assume that's true. So we can say that 3k minus 1 is a multiple of 2m. So this is a multiple of 2. But also observe that, or in this case, we can also substitute for 2 in this equation for 2m if we want to. But I'll just continue on a little forward, same with this. So observe that 2 times 3 to the k is a multiple of 2. So that would also mean that the whole equation over here, the whole thing is a multiple of 2. So multiple of 2. So this is true. So also by induction, (3n minus 1) is a multiple of 2. So there we have it. Now let's go over one more example. Now let's take a look at one more example. And this formula here is also known as the summation of odd numbers. So we must show that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. So do the same thing. You do the same as before. Use induction. So prove the base case n is equal to 1. So just plug in. So plug in 1 for n. So 2 times 1 minus 1 equals 2, 1 squared. And this will give out 2 minus 1 is equal to 1 squared, which is the same thing as 1 is equal to 1. So n equals 1 is true. So now let's do n equals, now let's show for n equals k. So now just plug in. So 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 equals k squared. And of course, an induction hypothesis, let's assume this is true so that we can show for the case for n is equal to k plus 1. So now n is equal to k plus 1. So now what do we do? We just plug in the following again. 3 plus 5 plus dot 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 2 times k plus 1 minus 1 is equal to k plus 1 squared. So how do we do this? Well, we have from the induction hypothesis right here that 1 plus 3 plus 5 plus dot 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 plus 2 times k minus 1 is equal to k squared. So let us use this assumption to manipulate the equation in order to prove the k plus 1 is true. So let's use the induction. So what we can do is we can actually add k plus 1 to both sides of the equation. So using the induction hypothesis, so that what we have is right here. So 1 plus 3 plus 5 plus dot 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 plus, use induction hypothesis, 2k minus 1, then add this term to both sides, plus 2 times k plus 1 minus 1 is equal to, use this, k squared, then add this same term here to the other side. So 2 times k plus 1 minus 1. Okay. So, and the rest should be simple from here as we're just using some algebra to solve this. So now we have that k squared. So now we have k squared plus, using distributive properties, we have 2k plus 2 minus 1. And we have k squared plus 2k, then plus positive 2 minus 1, a positive 1, and you can factor this out, so we get k plus 1, then k plus 1, also known as k plus 1 squared, as also a perfect square. And what's this? This actually matches exactly with the one on top right here, so this is true. Same thing for n equals k, same thing for n equals k. This is also true. So now, by induction, 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equals n squared is true. This formula here is true for all natural numbers in n. There we have it. That is mathematical induction right there. All right, now let's try. Now time to switch perspectives. So there you have it. That was mathematical induction. So what did you guys think? Did you learn something new? If you did, leave a comment down below. Honestly, this was an interesting topic to teach because it's actually one of those topics, if you are taking an analysis class, this is actually one of the first things they'll teach you, mathematical induction. It's a way of trying to teach you how to use your critical thinking and proof of a certain property with using natural numbers. It's more of like, let's test these numbers out to see if the property is considered valid for like all cases of natural numbers. So that's pretty much gonna wrap it up. If you enjoyed the video, give a like, subscribe to the channel, and leave a comment down below. You can feel free to watch any of my old videos that I did in the past, and last week I actually just released a video on the explanation of why the square root of 2 is an irrational number. You should definitely check that out. So that's it. So thank you guys so much for watching, and I'm gonna call Domino's Pizza because I've said Domino's so many times in this video and I have not eaten anything yet, so just give me 1 second. Hi, yes, I like to place a carry-out order. Yes, can I get 1 order of the ultra pepperoni pizza? And can I also get an order of the barbecue wings? Yes, that'll be it. My credit card information? Yes, I got that. So the credit card number is... How long? 15 minutes? Okay, yep, that sounds like a plan. Alright, thank you so much. Alright, off to Domino's.